Hi everyone. We're going to start with a game where we're going to learn to classify objects that are ISA and non-ISA. In order to do this, we're going to train ourselves to make this classification using some examples. So here's an example. This is an ISA, and this is not an ISA. This is not an ISA, and this is not an ISA. However, this is an ISA, and this also is an ISA. So what we've done, or what we're doing, is we're training ourselves to learn what is an ISA in order to do this classification. And we're doing this by creating an abstraction or a model, right? We're trying to abstract away some features that'll help us categorize objects as ISA and non-ISA. And we do this by using data. So we have this data set of objects. And not only do we have just data, but we have labeled data, meaning that we have the object, the square there on the left, and we have its label that it's an ISA. So we need that labeled data in order to do this training. So in order to learn what is an ISA and what is not an ISA. And once we do that, once we complete that phase of training that we've learned how to do this, now we can use that training in order to do inference. That's sort of the second phase of this, where we can make predictions as to the label or class of an object. So we can make a decision, is that first one that we see there an ISA or not an ISA? And I think you'd say, well, that's not an ISA. The second object, we haven't seen that shape before, but I'm hoping you'll think, yeah, that's an ISA. It's likely to be an ISA. The third object, that green circle, I'm pretty sure everyone will say that's not an ISA. The fourth one's a bit trickier because it has that dotted border, but if you guessed ISA, you'd be correct. And the last two are not ISA. So what we've done is called a classification task, and the first part of a classification task is training using labeled data. So we have that labeled data set, and we're learning to make, well, what is an ISA? We just have some set of examples, and we're making that abstraction or building a model. And once we do that, we can use inference to classify new instances. So we can see new objects and make these labels. And when we have a machine learning task that uses labeled data, that's called supervised learning. So supervised learning simply means a machine learning task that uses labeled data. And machine learning with unlabeled data is called unsupervised learning. And we'll see an example of that later on in this course. Here's kind of a diagram, or this is a diagram of what we've done. So we started off being untrained, or we have this untrained model, and we have a labeled training data set, and that's the training process where we're untrained and we take this labeled training data, and through some process we've created a trained model in our brain of, what's this model, what's this abstraction. Once we have this model, we can then use inference, the part from the trained model onto predictions in this little chart. And for that, once we have the trained model, we can take unlabeled data and through an inference process make predictions. So for now, for our first adventure into machine learning, we're going to ignore the training part and just focus on, once we have a trained model, how can we use it to make predictions? And doing this is called using a pre-trained model. Someone else has trained the model for us. And the model we're going to be using is called LXNet. This is no longer a state-of-the-art model. It was developed about 10 years ago. During the time that 10 years ago, it took 6 days to train the model. So you can see that using a pre-trained model is well worth it. It would save us a bunch of time. Even today with modern hardware, it would take us a while to train this LXNet model. And what LXNet does is it recognizes images and it classifies them into one of 1,000 different categories. Here are those categories, and the print is small, so let me just highlight a few of them. It can, when it sees a picture of a standard poodle, it knows standard poodle, box turtle, German shepherd, grasshopper, brown bear, bathtub. The list goes on and on. The face powder, espresso maker, an envelope. So let's actually start coding. We're going to go to collabresearchgoogle.com and get started. Okay, let's go to that site. The address again is collab.research.google.com. So your display will look different than this. When you first go to Google Colab, you'll see a welcome page. And I've been to Google Colab a lot. I don't see that welcome page. So let me just cancel out of this. And let's all go to File, Open Notebook, Examples, Overview of Colab Features. Let me just close that part. So what we're looking at is a Jupyter notebook. A Jupyter Notebook is a web-based interactive computing platform. Web-based, we're looking at it in a browser, interactive computing platform. We're able to write and execute Python code. What Google Colab is, it's a hosted Jupyter Notebook service. Hosted meaning it's running in the cloud, so we have a virtual machine associated with this that's actually running the server that's presenting these pages to us. We could download some server application to our laptop and just run everything locally so we can be off-grid somewhere nice and work on our tasks. But the advantage of Google Colab is it has GPUs, has graphics cards. That the graphics cards in laptops are pretty deficient. Our code would run slower. At least our deep learning code would run slower. So it's a good idea to be working on Google Colab, or it's an advantage to work on Google Colab. So Jupyter Notebooks consist of cells. A cell can contain some explanatory text, as it says, or executable code. In these explanatory text cells, you can have text, obviously. You can have images, videos, graphs, equations, a host of things to explain what you're doing in your Jupyter Notebook. It's really quite cool. And executable code. To edit a text cell, we just double click it, and then we get this editable feature. This is in a language called Markdown, and we can create a secondary heading. Let me just call it heading 2. A tertiary heading would be with the 3 one, heading 3, and just some general text. And to close that editing window and just see the results, it's Shift-Enter. Let me just scroll up a bit, and you see what we did here. The other option are code cells. That's over here, this A equals 10, and what's the value of A? And to execute that, not surprisingly, it's Shift-Enter. I keep scrolling up, and I get the answer 10. Let's add a cell. I can do that by this up here. And let's say I want to compute seconds in a day. And this probably will also show us the value of autocomplete. There we go, seconds in a day. And it filled it in for me because I've been doing this before. So seconds in a day equals 24 times 60 times 60. What's the value of seconds in a day? And we get that. So that's the basic idea, or a very quick overview of the idea behind Google Colab. Text cells, code cells. And it pays to read through this introductory or overview of the features involved. And I'm not going to do that here since it's already presented to you. So now let's go to the first thing we'll be working on and submitting, which to do that, we'll go to File, Open Notebook. And now we have this choice here. We're going to go to GitHub. And it's already, because this is my account, it already knows who I am. But we're going to go to, all of us, go to Zaharsky, ML class, and hit return there. And we're going to find this Quick Start Lab, which is right here. I'll click that. It asks me whether I want to leave the site. There's that. Yes, I'll leave. And just to reiterate, so if I want to see how there's pictures here. If I want to see how I did all this, I can just double click this cell and you'll see how I created a link. Again, this is in Markdown, and you see how I added some pictures to that cell. Not that important. So what we did was we uploaded this Python notebook Quick Start from my Zaharsky Git repository, and what we need to do is save it to our own. So we have some options here. We can go to File. We can save a copy in Drive, which might be good. The advantage there is that it will automatically save copies to Drive, or save what you're doing to Drive as you're working on the notebook. So you don't intentionally have to think, oh my gosh, I have to save this to Drive. And at the very end, when you're ready to submit your work, you just send it off to GitHub. Another video shows that. Or you can just save a copy in GitHub and right to start with. Let's go with that option since this one's pretty easy to figure out. And let me just show you this slightly more complex method. So I'm going to save a copy in GitHub. Okay, so it's saying what repository to use. I definitely don't want to use that one. I'm going to use this demo one that I have. So you'll select the repository. And now we can give it a name. You can keep Quick Start. So I've already been using this demo repository, so I'm just going to give this a different name. I'm kind of running out of name ideas. I'll just call it and Quick Start. And I'll just call this first commit. Make sure you check include a link to Colab. Okay, so here I am in GitHub, and it's showing that I successfully added that Jupyter Notebook to GitHub. All right, let me go back here, close this original one, since I don't want to make a mistake and edit that one that's not saved. And here I am in GitHub, and I'm going to open in Colab. Okay, so here that is. And if I make a change here, let's say I want to just add my name, which is always a good idea. I called this person Ann Mulkern. And add a space there and save it. Or hit Shift Enter. And now let me go up. Apparently I lost everything. So I have my name, and I just want to save that to GitHub. And just, you normally wouldn't save after one change, but just for demo's sake, let's do it. So save a copy in GitHub. It's taking a while today. That all looks great. And now I can say some commit message that'll help me. Added that's kind of a dumb commit message. Include link. Okay. So here's an advantage of doing what seems a little bit more complex method than just saving it to Google Drive, is that if I make a mistake in my code somewhere, I deleted something that I didn't intend to delete in my code and want to go back to the previous version, easier to do with GitHub. So as you can see, that's pretty easy to do. So the goal of this quick start is to just gain some familiarity both with Jupyter Notebooks and get some sense of how these deep learning systems work, just doing some inferencing. We're not going to train a deep learning system. We're just going to use one that's already trained. And what we're going to look at are recognizing what an object is in an image. Here's just some examples you can read. Kind of laying out the strategy we're going to use. And we already covered this diagram, right? So we have this untrained model training process. And we have this, after training, we'll have a trained model. You can give it something we want to know about, like what's this picture, and it'll tell us. It'll make some prediction here based on inferencing. So I'm just kind of glossing over all this because you can read it on your own, no sense duplicating that information. So what the model we're going to use is called VGG16. And what it was very good at was not only recognizing what's in a picture, like standard poodle. That's not a standard poodle, but I made a little error there. And not only that, but locating where they were in the picture. So we're not going to do that. We're just going to recognize, hey, this picture is of a poodle. But that's what this system was extremely good at. When it was #1 in the competition in 2014. And the reason we're using such an old system, a 10-year-old system, is that it'll go faster in Google Colab than using a state-of-the-art system, which requires, pretty heavy computing resources. Okay, and we're going to set the runtime GPU graphics card. So to do that, we're going to go runtime, change runtime type, and here, depending on what you have, you'll have some options for GPU. So we do not want CPU. We want to actually use a graphics card. And let's just stick with this. These are kind of progressing in how good they are. This is the best one currently available for me, this A100. But let's just stick with this T4 for now. The code we're going to use, or the libraries we're using, are what's called TensorFlow and Keras. We'll learn more about these later. But the good news for us is that they're already available in Google Colab. They're kind of a hassle to set up on your desktop or laptop. I've done it, and I can verify that it's not easy to install TensorFlow, but luckily we can ignore it for now because we're using Google Colab. So the first thing we're going to do is load that VGG16 model, and we're going to do that with these two commands. So here's this line here. We're loading that library, that amount of code from Keras applications. So we're importing this VGG16 library. And this line, we're actually creating an instance of that VGG16 neural network model. Weights equals ImageNet. That simply means we're trying to recognize the 1,000 images from ImageNet. That's a historic data set that people use in these competitions. Include top equals true simply means what we're trying to recognize are those original images. So weights here are the pre-trained model. So I almost didn't execute that code. So as we remember, executing Shift Enter. So it's taking a bit of time because it's downloading that model and all the weights associated with the model. There, and we have it. We have this model. Now let's, I haven't done this in the code, but we can add a code line here. We can just say, well, what is that model? Let's go summary. It'll give us some information about So it gives us all the details about how this model looks. To us, this doesn't make much sense, but it will. So the total parameters are, what is that? 138 million parameters that have already been trained for us rather than we're training them. All right, so this just explains what I was trying to explain. So what we want to do then is give it an image. Now that we've created this model, let's go up here again, and we called it, I am going way up, sorry, model, right? That was the variable name we gave it. So we want to use that model and give it a picture like this, and we want it to say, hey, that's a picture of a standard poodle. So let's first download the image so we can look at it, and that download command is here. We're getting it from my account, and we're just going to save it locally to this machine, this virtual machine running in Google servers. So here I'm going to execute it, Shift Enter. And there we get it. And if I click on this file icon, I'll see that I have Poodle JPEG loaded. Let me close that. This exclamation point or bang is, if that occurs at the beginning of a line, it just means interpret this line as a Linux command, not as a Python command. So let me just add another code cell here. If I go bang ls, I'll get whatever the content is of that directory. And if I want more information about the files, I can just go, give me all that information, and it'll give me that information. So a bang in front of a line simply means execute this as a Linux command. All right. So now let's load that image into Python using a library, this PIL library, the Python image library, and just send that image to a variable called image, which that was fast, and we can display the image. All right, there, finally. All right, so there we have a picture of a poodle. It's my poodle ghost, which I think is behind me. So that image, as this says here, is over 4,000 by 3,000 pixels, so 12 million pixels. And this VGG16 model was designed to work with images of size 224 by 224. So we need to kind of transform this image to that size. So we could just make the image in that size. We can just transform it. But if we just said, hey, make that image 224 by 224, we're going to get this squished looking image. Now this will probably work fine. I don't think it should affect us too much, but I just don't like it. It just doesn't look good to me. So we're going to do a kind of a two-step process here. The first thing we're going to do is resize the image so that the smaller dimension is going to be that 224. That'll be this one. So obviously this length is going to be bigger So what then after that step of just resizing this image, so the smaller side is 224, I'm going to crop that image. So, oops, that was the wrong thing to do. I'm going to crop that image so it's smaller. So I'm just going to remove the left and right sections of it. So again, let me just repeat. So instead of squishing that image by saying transform our nice huge image into a square image of 224 by 224, I'm going to first resize the image to reduce its size and then crop it. So now I'll end up with a square image. And there's actually one command that'll do it, which is this one. This Keras utils load image, and you give it an image file here. You can say what your target you want it to be, 224 by 224. And if I say keep aspect ratio true, that means don't swoosh it down, but rather crop it to the right size. So that's convenient. That's kind of cool that we can do that. So let's go ahead and do that. Okay, and now I have this image, and I can say, what does that image look like? And you can see that's exactly what I want. And that size, I can say, what is the size of that image? It's 224 by 224. Great. So now we have the model we loaded that was pre-trained, and we have the image we loaded, and we got it down to the right size, 224 by 224. Okay, and now we need to convert that image into a form that'll be accepted by VGG16. First, VGG16 expects an array, not this image data structure. So to do that, we're going to import this preprocess input, this Keras library, this library called image. And the first line that's of importance is here. So we're just converting that image to an array. So that's simple to understand, I hope. Now what Keras, what VGG16 expects is not just one image, but an array of images. It wants to make predictions on a group of images, not just a single image. So it's expecting an array of images. So what this line does is do that. So from one picture, it's going to make an array of one picture. So to do that, let's just print some information here. So the first thing I'll print is this input image shape. So it'll tell us what the shape of that array is. Sorry for messing up my... And I'm going to do that same thing after I change it into an array of images. Just leave that be here. Okay, looks good. And after I make that array, the next thing it does is that VGG16, and this one's specific, this preprocess input is specific to VGG16 up here. It's going to process that information, or it's going to process the numbers in that array and convert them, transform them into a form expected by this VGG16 model. So the first thing we're going to do is change the image to an array, and I'm going to print the shape of that array. Right, so that we would expect would be 224 by 224 by 3, red, green, blue values. And then I'm going to add that or make an array of images by this command here. And then I'm going to print that shape again. And so that shape now should be, it contains one image in that, or one row, let's say if each row contains an image, one row, and that row contains an image which is 224 by 224 by 3. At least that's my prediction. All right, so let's go ahead and run that. So here we have the result is that shape, as we predicted, would be 224 by 224 by 3. That's converting the image to an array. And up here, when I expand this dimension, I've added this 1 here, which means now I have an array that consists of each element will be 224 by 224 by 3. All right, so now we have this input image, which is in the exact format needed by VGG16, our model. And here, finally, we're getting, even though this is actually quick, if I wasn't explaining it so long, it's going to make predictions. So I just say model. That's remember the pre-trained model that we created. Dot predict, obvious good function to have, and we give it that image that we've been working on. And oh my gosh, we just have a series of numbers as predictions, not something say, hey, this is a standard poodle. And these are the predictions or the probabilities that the image is of these 1,000 different categories. We don't know what the category names are quite yet, but those are the probabilities. So whatever this one is, this first number, the probability, oops, it's not the first number. Let me get way to the top here. This first number here, that probability is way low that it is whatever that object is. All right, cool. And let's look at the shape of that. So we have an array that's the first image, 1, and it has 1,000 different values, the probability of each of those 1,000 different classes. Okay, and these are the numbers of those, the first 5 numbers, and they represent a tench, which is a fish, goldfish, a great white shark, tiger shark, and hammerhead. So it's great that our model thought this wasn't a fish or a shark. So what is it? So now we have yet another library called Decode Predictions, and it'll give us the top 5 predictions for that model. And there we have that. It thinks it's 86% or almost 87% confident that this is a standard poodle. The next option is a miniature poodle, and it goes on from there. So that's great. It looks like what we created predicts very well what this image is. Before we try another one, let's kind of combine everything. All this code was pretty well spread out in the notebook, making it hard to see what the whole thing was. And I'll do that in 2 blocks here. So this is creating, first putting all the libraries together, which is always a good standard in programming standard. And then we create that model that we did before. So let me go ahead and do that. And there, that's done. Now let's put all the code we had related to an image into one function. So this is the transformation function, and it's going to load the image and crop it, convert it to an array. So we've seen all this code before. It's just in one place now. And then finally I have this prediction function. It downloads the image from the web, makes a local copy of it, and it's going to transform that image. This execute this code up here, and finally give us the top 5 predictions. So let me I'm sure I execute this code. So it's Shift Enter again. Okay, and now let's hope I did everything right and see if we can recognize this violin, which I got from this website. So let me just go to that website if I can. And it's a violin. That's always good. And now let's do the Shift Enter to see what it thinks it is. So it's 93% sure it's a violin. Way cool. We can find out what the 1,000 labels are by running this command. It's just a file I have on my. So these are all the 1,000 things the ImageNet can recognize. So a trench coat, a wallet. There's, I think, 100 dog breeds or something like that, I believe. So you can look through here if you're trying to experiment on your own and seeing if, it knows what I don't know what half of these things are, but you can give it a shot. So electric guitar is a part of the image. There's an electric guitar picture, and let's see if it works. That looks good. 75% sure almost that it's an electric guitar, and an additional 21 thinking it's an acoustic guitar. So it's pretty confident it's a guitar, and very confident it's a guitar, and pretty confident it's an electric guitar. So that's pretty sweet. All right, so here at the end, I have what you can try with using your own image. And here is a little bit more challenge you can read about. After you're done with this, don't forget to File, save a copy in GitHub. I don't know why it's taking so long today. Okay, so that's my file. And now I'll make a commit message. And I'll say added code for, this is part of what you'll be doing. That looks great. And okay, I think we're good. All right, so that was it. I hope this helped a bit. So again, what we did was, let me zoom up here. This was the simple part actually. We uploaded to our Google Colab the VGG16 pre-trained, so that's what all these weights were, and we say, hey, actually try to predict the original 1,000 labels, and we created this variable called model. We decided on an image. For me, it was this poodle image. And to use this image, we had to convert it to a form that was recognizable by VGG16. Remember that VGG16 is 10 years old, so it recognized only pretty small images, that 224 by 224. So a lot of what we talked about was converting that image to a much smaller image. And finally, we made predictions, right? We said, hey, predict what this input image is, and put it in English by saying, where's my prediction here? Decode predictions. So I hope that was helpful to get you started. If you have any questions, contact me via Slack. Good luck on all this. Take care. Bye.